Section 3, we're going to be mostly looking at periodic properties or periodic trends on the periodic table. So we're going to be looking at things like ionization energy, atomic radius, electron affinity, and electronegativity. The first trend we're going to look at is atomic radii, and we should be able to figure out that trend just from looking at this graphic here. So we're going to be watching for what happens to the radius of the atom as we move across a period or down a group. I have a short video clip we're going to watch, and then we'll talk some more about this.
It is possible to estimate the radii of atoms in characteristic bonding situations by observing the distances between atoms in molecules. In any given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
Here's another way of looking at this. On this one, we can also see this trend that within one period, let's say within period 4, as we move across the period, the radius tends to decrease. But as we move from period 4 to period 5, we can see overall our radius tends to increase. Next we have ionization energy, which is the energy it takes to remove an electron from a neutral atom. We're going to watch a few short video clips for this one.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and a greater effective nuclear charge. Thus, each successive ionization requires more energy. This graph shows the way in which the ionization energies of the aluminum atom increase as successive electrons are removed. Notice that the ionization energy increases with each successive removal of an electron. However, there is an especially large jump in the energy required for removal of the fourth electron. From a knowledge of the electron configuration of neutral aluminum, can you account for this dramatic jump?
The first ionization energy is the energy required to completely remove an electron from a neutral atom. Ionization energy generally decreases as we move down a group because the outermost electrons are increasingly distant from the nucleus. Less energy is required to completely remove the first one. As we move from left to right in a given row, the ionization energy increases dramatically because of increasing effective nuclear charge. Notice the periodic character of the change in ionization energy as we move across each row. As we move across the first transition element series, the ionization energies increase slowly in proceeding toward the right. The same trend of increasing ionization energy across the transition series is observed in the second long row, consistent with the periodic character of this property.
This chart here shows you the overall trend. This might be something good to jot down in your notebook. Next we have electron affinity, which is the energy change that happens when an electron is acquired or when the atom gains an electron. Again, short video clip, and I would jot down this graphic in your notebook.
The electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For most neutral atoms, energy is released when an electron is added. Because energy is lost from the system in such a process, the electron affinity is a negative number. The electron affinity declines slightly as we move from hydrogen to rubidium in group 1 of the table. The electron added to the neutral atom in each case is paired with the one valence shell electron already present. A similar trend of slightly decreasing values of electron affinity with increasing atomic number is also observed among the halogens. However, the values of electron affinity are much larger than for the alkali metals. The values of electron affinity vary irregularly as we proceed from left to right in a given row of the table. These apparently erratic variations can be accounted for in terms of the electron configurations of the atoms. For example, when an electron is added to chlorine, it occupies a vacancy in a valence shell orbital and thus experiences a significant effective nuclear charge. The process is thus exothermic. When an electron is added to an argon atom, which already has a filled valence shell, it experiences mainly electron-electron repulsion and is effectively shielded from the nucleus. Addition of an electron in this case is an endothermic process.
This next one is ionic radii, which is a little bit different than the atomic radii. Ionic radii is the radius that your atom has when it becomes an ion, so when it becomes charged. It's either going to be a positive ion or a cation or a negative ion, which we call an anion. And the thing to think about with this one is, to become an ion, your atom has to either gain an electron or lose an electron. And electrons, you remember, reside on the outside of your atom. So if you're taking something away from the outside of the atom, that's going to make your atom smaller. So positive or cations tend to be smaller than their neutral counterparts. Anions, on the other hand, become negative by gaining an electron. So you're putting something on the outside of the atom. So we're adding to the outside. That's going to make it bigger. So anions tend to be larger than their neutral counterparts. Now these outermost electrons that are either gained or lost are called the valence electrons, and we remember that those reside in the S and P sublevels of your highest energy level. The next trend we're going to look at is electronegativity. Here is your overall trend for electronegativity, and here is your definition for electronegativity.
The electronegativity of an element is a measure of the capacity of the element to attract electrons to itself in bonding with other elements. Electronegativity increases as we move from metallic to non-metallic in character, that is, as we move from left to right across the periodic table. In the first long row, we see a gradual, though somewhat uneven, increase in electronegativity as we cross the first transition element series. Note again that metals have lower electronegativity values than nonmetals, consistent with our observations that metals tend to give up electrons in bonding with nonmetals. Within a given group, electronegativity generally decreases as we move downward in the group.
There's also a table in your book that has a lot of values for electronegativities. That's something we're definitely going to be using. It is probably something you might want to jot down in your notebook as well. And that is it for today.